So this is week three for this night class. In case you happen to not hear me clearly, just alert me so that I'll be able to raise my voice up or something. Or if you don't see my screen, just give me signal so at least I'm not really seeing your chat, so it will be best to turn on your mic and say something so I'll be able to hear you. So let's head on. So this today's topic is kinematics, and for our objective will be studying motion, um, types of motion, and projectiles. So these are like the areas we'll focus on in today's lesson. Let's just head into the new lesson. I don't know you if you were in the last class and you probably had questions. I don't know if you had any question that we could go and revisit them before we move on. But if not, I'll just like you to just tell me to go ahead. Can I go ahead into today's lesson, or you have questions from last classes?
Yes, sir. Yeah. You can go ahead, sir.
Okay, okay. So let's move on. So this is the lesson outline. We'll be learning, as I was saying initially, we'll be learning types of motion, linear motion as a type of motion. We'll focus on linear motion, and we'll look at graphs of motion, then free fall and projectile. That'll be capping our lesson for today. Let's just head into topic. So what is kinematics? So as the name implies, it's kind of an involvement with kinetic energy and the study of motion. So as I have here, it's a branch of mechanics concerned with objects in motion without regards to the forcing the motion. So there are some aspects or some branches of physics or some topics in physics where you would talk about you talk about mechanics, and you would also put into consideration the force that is causing this motion. So while kinematics is not, you would not regard that force that is responsible for the motion. So repeating myself, I'm saying kinematics can be defined as a branch of mechanics concerned with objects in motion without regards to the force causing the motion. So the main focus will be to describe how things move, and we'll be focusing on displacement, velocity, acceleration, and time. So I know that we, all of us, so long as we are humans and we are living things, we move. That's one of the characteristics of living things. All living things move. So there are different reasons why
Okay.
people move, and there are different forces. Different things can make people move, whether you're moving physically or any other interpretation of movement. So
Yeah.
movement is when you talk about movement, you're talking about a change in position of an object or of a body from one point
Okay.
to another. Say you cannot say a body has moved except it's changed position from one point to another. And this change of position might not be necessarily um, all parts of that body that's changing position entirely. But so long as some part of this body is moving or is changing, you can say that body has undergone motion. So
Okay.
um, there is what we call displacement, which is the measure of the change in distance. And there's what we call velocity, which we treated in, I think, our previous class, where I said velocity is different from speed. And I was saying that when you make mention of direction, that's when you're talking about velocity. But when you just talk about the rate at which a body is changing position, you're talking about speed. They have the same units. So without going back,
Yeah.
um, we, we will be focusing on quantities like displacement, velocity, acceleration, and time. So acceleration is the what I call it, the upper version of velocity. So
Velocity.
let's do some serious stuff. So I have here my definition for displacement. So it is the change in an object's position. Change in an object's position. So when we're talking about vectors and scalar quantities, I remember mentioning that distance is a scalar quantity while displacement is a vector quantity, because displacement, when you mention displacement, you talk about a distance, a body moving from one point to another and in a particular direction. So that's what displacement is. So as I have here, I said it's a vector quantity and it has both magnitude and direction because of it's a vector quantity. So the formula for calculating displacement is you take into observation the initial position of that object. As we can see here, sorry, as we can see here, sorry, let me see. As we can see here, let me put on my illustrator. As we can see here, we are seeing that we have change in distance or change in position, which is used to represent displacement, is equal to the final position of an object subtracted by the initial position. So xf means the position at the final point to the position at the initial point. So it's also called change in position. The displacement, formula for displacement is final position minus the initial position. That's how we calculate displacement. So I have an example here which says traveling 12 meters to the east is an example of displacement. So well, assuming they just say traveling 10 meters, the body travels 10 meters, you are actually giving the distance that body covered, not the displacement. So, but when you talk about the direction towards which the body moves, you're talking about the displacement. So, moving on to the next on this, we talk about velocity. So, there is this form of progression that should be taken into recognition. There's this kind of progression that happens when you're talking about motion. You'd always move from distance or displacement up to up to velocity and speed. Then next, after velocity and speed, you graduate up to acceleration. You get, so there's this kind of progressive movement where you start from the distance or displacement, and you move upward into the velocity or speed, then moving upward into acceleration. So this sequence of arrangement is important. We would need to take account for this sequence because it would help us later or give us a kind of understanding of things later when we go deeper into the course. So velocity, unlike displacement is the rate of is the change in position of an object. That's what displacement is. You can see here. However, velocity, the rate of change of displacement over time. So for velocity, for displacement, we just talked about this position. We just talked about position, change of position. But now in case of velocity, we talk about change in displacement. You see, velocity is taking account of displacement, like what I can call the younger brother. It's not really the younger brother, Sha, but I would just like to put it that way. Um, Position is the last born. I'll put it like position is the last born. Second to the last born is displacement. Then the elder brother of displacement is velocity. Then the most senior brother is acceleration. So this is how the flow moves from position to displacement to velocity, then acceleration. So now displacement with position does not really have a definition per se. It's just a point in space. That's the definition. It does not really have a formula. But now when you graduate from position now to displacement, when you are involving two positions, you then talk about displacement or distance. So then when you graduate further, you then talking about displacement with respect to time. Displacement with respect to time, that was velocity. It is the rate of change of displacement over time. So it can be written as displacement delta x divided by change in t. So you can see some formula that will say it is xf minus xi all over tf minus ti, meaning the final position minus the initial position all over the final time minus the initial time. That's what change imply. When you see change or delta, it means final minus initial. So velocity can be calculated using the formula delta x over delta t, meaning change in position or displacement over change in time. So that's the formula for velocity. I believe this thing should be something that we probably are used to already. So let me not dwell too much on this. So the example I have here, I said traveling 12 meters per second is an example of velocity. So it's just trying, what this is trying to talk about is that you're mentioning a distance or a displacement, and you also mention it per time. So when you see a distance being measured per time, it's talking about the velocity. It's usually distance or displacement over time. When you talk about distance over time, that's speed. When you say displacement over time, that's velocity. So I'll be interchanging it. I might use distance for displacement or displacement for distance, and I might use velocity for speed and speed for velocity. So in case I'm changing between them, so just don't get confused. Except when it is important, I'll then specify, okay, I'm trying to make a difference between both. So as you can see here, the example, we are talking about 12 meters per second. That is 12 meters divided by 1 second. That's a measure of displacement of velocity rather. So there's another thing that is called average velocity. Average velocity. So average velocity, unlike the normal velocity, it is average velocity is calculated by the sum of the whole velocity, the total velocity, divided by the total time. That will give you the average velocity. The total, you're not taking final minus initial now in this case of average velocity, you're taking the sum of all displacements divided by the sum of all times. You get, so that's different between normal velocity and average velocity. Average velocity is taking into account the total displacement divided by the total time, while normal velocity is just the change to the change in time. Let's move on to the next slide. On to the next slide. We have types of motion. So there are basically four types of motion. Four types of motion, generally both in physics and in chemistry. So we are focused today on physics. Four types of motions we have. It's one. I would like to start from the bottom. The first one is random motion. I like starting from the bottom, or I prefer starting from random motion. The random motion, which is also known as Brownian motion, is when an object moves without any specific pattern. It's just moving zigzag, like something like this, just roaming around without having a specific direction, a specific maintained direction. I would say it that way. That does not have a specific maintained direction or cannot trace its pattern of movement. Just like this, you don't know where my illustrator will be moving next. Just know that it's moving around the screen. So this is an example of random motion. I'm usually observing gas molecules. Observing gas molecules. So next is vibrational motion. So we've seen how phones vibrate, and even in the diagram of a vibrating phone, they would always show it like as though it's just moving from left to right. So it's usually a two-directional motion. It just moves left to right or forward and backward. It's just a repeating kind of movement, either left to right, forward, backward, up, down. Just a continuous single direction motion. It's a form of linear motion though. So it's the kind of motion that we see when we pull a pendulum bobble. Let me say you use a single thread tie, maybe you use it to tie your shoe, or you hold your shoelace with your shoe on it. Then you tie it somewhere, then you pull your shoe backwards and leave it, let it dangle by itself. You see that movement moving to and fro. It's an example of vibrational motion, though it does not look like the common vibration we know, but this is how these are how vibrations always move. It's always in a to and fro movement. It gets to a point, pause, come back to another point, pause, return back to the initial point, pause. That's just how it is moving. It's moving to and fro, just like the devil, as they said sometimes in the Bible. So that's a vibrational motion. It's always a movement to and fro. So the third type of motion is um, rotational motion. It's rotational motion. So as the name implies, we know what it means for something to rotate. So when something is moving um, about an axis or in a circular pattern or in a circular path. So this kind of motion where an object moves in a cycle along a circular path is called rotational motion. And when it's moving along a circular path, it means that there is a center axis which it is rotating about. There's always a center axis is rotating about. When we move to the next slide, probably we'll see an image that illustrates these types of motion, most of these types of motion better. So we then have translational motion. This is just a motion in one direction, a motion in one direction. And I think this is the type of motion that humans prefer. Nobody likes to be almost stagnant. So nobody likes to have a vibrational motion where it's just moving forward and backward. Is if you go forward today, come backwards today, go forward today, come backwards. That's not what humans like. Someone going in circles. I know people say, God forbid I'll go in circles. People don't really like rotational motion. Humans don't really like rotational motion. Or translational motion, meaning you start from a point and you keep on going in a particular direction, specific direction. So this is called translational motion. And it's also called linear motion. The translational motion is moving straight towards a direction. So moving straight towards a direction. Rotational is moving about an axis in a circular path. That's rotational motion. Then vibrational motion is moving to and fro like the devil, just forward, backward, forward, backward, forward, backward. That's vibrational motion. Then random motion is one that you don't even have forehead, you don't have back, you're just moving like just scattered, a scattered form of motion. So these are the types of motion. So let's see an image trying to depict these motions. So as you can see, this image here, we can see they spoke about just three of those type of motion. They did not include the random motion or the Brownian motion. So this under vibrational motion, we have three types of vibrational motion. In under rotational motion, we have two types of rotational motion. They are actually the same thing, but they look similar. They are the same thing, but they have this different orientation. So then we have what they call it, transitional motion. So I will start from the transitional motion. You can see this image, they pointed a direction. It's just something that is either falling downwards or moving upwards or moving to the left, just a specific direction. There's always a specific direction and it's changing position continuously in a specific direction. That's what transitional motion is like. So, however, see this what we have here under rotational motion. This one here is talking about moving about the x-axis. So this is an axis, the horizontal axis. And you see the arrow that they use to indicate moving around this axis, this axis here. So this is assumed to be an horizontal line. Then this object is moving about the axis, just like this, moving about this axis, this straight axis is moving about it. So while this other one now is, we have the horizontal axis and it is moving circularly about it, moving circularly about it. So that's these are the types of rotational motion. Rotational motion, they are usually about an axis. Then now we have vibrational motion. We have different types of vibrational motion. We have the bending motion where it will move up, come down, move up, come down. Both sides are moving up like this side, as this side is going up, this side is going up, this side is coming down, this side is coming down. Just like bending up and down, bending up and down, bending upwards, bending down, holding downwards, bending upwards, holding downwards. That's what this kind of vibration is a form of vibrational motion because it's a to and fro movement. This one now is symmetric stretching, where the center is static, but it's just spreading this way. This one is spreading this way. So because it's going to and fro, it's also characterized as vibrational motion. So now, it can also be that it's not a symmetric one where it's not both of them are not moving at the same time, the same direction. It will be this one will move this way, come back, and the other one will move the other way, come back, or just one will be moving in one direction. So this is also a form of vibrational motion. So the takeaway from or the defining factor of these types of motion is vibrational motion has to do with to and fro movement. As long as the movement is to and fro, just moving forward, coming back, the to and fro movement, you can tell that that motion is a vibrational motion. When the movement is moving about an axis in a circular path, obviously it's a rotational motion. And when it is moving in just a single direction, not without returning back to where it started from, just moving towards the direction continuously, it's translational motion. Then binary motion is the other easy one that we should know. Now let's go to linear motion. As I said at the beginning, I said the focus would be on um, linear motion. Focus would be on linear motion. So what we have here, we said linear motion involves movement in a straight line. So linear motion is an example of translational motion, as I just explained before. So it's usually a movement in a straight line. So the key quantities that are using that are usually involved when you're talking about linear motion are speed, velocity, which are like brothers and sisters, then acceleration. Speed, velocity are like brothers and sisters, but they're mentioned in the same unit. One of them is just a scalar, then the other one is a vector. Speed is a scalar, then velocity is a vector. So these are the quantities that we'll be focusing on as we talk about linear motion. Let's move on to the next slide. Sorry. So trying to define speed. We know that speed is the distance traveled per unit time. The distance that an object travels per time. It's not, you don't need to pay attention to the direction which the object travels. You just need to know that we covered a distance as time was changing. So it's usually a distance covered per time. And the formula for speed is distance over time, as we know, and it's measured in meters per second. It's measured in meters per second. So you could see a question under speed, or under speed, they could tell you, okay, um, something or an object travels or covers a distance of maybe a ship covers a distance of 300 kilometers for 9 hours. Calculate the speed at which it's used to cover this distance. So what they're just trying to tell you is, okay, do the division of distance divided by time. It's just that simple. That's how velocity is on the basic level. So we'll be moving forward probably later to some other advanced way to calculate velocity or speed. So usually you just need the distance and the time it took it to make that change in position. So the formula, using that formula, this example will be very basic. Just dividing 120 by 6 and you'll be able to get your speed in meters per second. So in cases you were given where you were given speed in kilometer per hour, as we taught in one of our initial class, I guess our week one, we were taught different units where we said preferably people would prefer that things are represented in SI units. So if you are given your meter or your length in kilometer and you're giving your time in hour, that's not SI units. So it will be best you convert from kilometer back to meter, then you convert from hour back to second. So if you can remember, there is this conversion format that I use. So you could see the video on YouTube, the week one video where we talked about this conversion. See the video on YouTube. I believe it's a clear video where I explained using a simple pattern on how to calculate or how to convert things from different units, from either kilometer, centimeter, and so on. So that will be in our week one video. Let's move on to the next slide, velocity. So the sister of or the brother of speed is velocity. Velocity is similar to speed in that it's measured in meters per second, the same with speed. But now velocity is not just a measure of distance with time, but now displacement with time, meaning it takes cognizance of the direction at which the distance was being covered. So the formula is displacement over time. The formula is displacement over time, and it's measured in meters per second. So now let's see how a typical velocity question or a basic question under velocity look like. It could tell you a car moves from or it moves 30 kilometer due east or 30 kilometer towards the east or 30 kilometer in a particular direction in 5 seconds. So calculate the velocity. So once they've told you calculate the velocity, sometimes you might not even need to be told that it's the velocity. So long as you just check and they find out that you found out that from the question they mentioned the direction at which the object is moving. You just know typically that what they're talking about is not speed or velocity. If they don't mention the direction, then you know they're talking about speed. But whether it's speed or velocity, they are almost irrelevant. The difference is almost irrelevant. So let's move on to the next slide. We have acceleration, the elder brother of velocity and speed. The elder brother of velocity and speed. Going back to how I started, I said position is the last one. Second to the last is displacement and distance. They are twin. Displacement and distance, they are twin. Then we have their elders, which are also twins, velocity and speed. Then we have their most senior, which is acceleration. It's not a twin. Acceleration and position, they are not twin. They are the first and the last one. While distance and displacement, they are twin and they are the third one. Then what they call it, velocity and speed, they are the second children and they are twin as well. So acceleration, it is the change in velocity with time. So velocity is changing distance, that is changing his younger brother with time. So now all of them, like acceleration now will be changing his own immediate younger brother with time. That's changing velocity with time. While velocity is changing its immediate younger brother, that's displacement with time. So displacement over time gives you velocity. Velocity over time gives you acceleration. It's just that flow. Displacement over time gives you velocity. Velocity over time gives you displacement. Displacement over time gives you velocity. Velocity over time gives you displacement. So this movement pattern is important that you should take note of it because there's this kind of understanding that you get once you are giving questions and you have this picture in your mind that they have this flow from acceleration down to velocity, then from velocity down to displacement, then displacement down to position, then taking it backwards is how you'll be able to find the formula. So from velocity is where you would start seeing change with time. Acceleration also change with time, but displacement is just change in position. You don't need to pay attention with time. So let's move on to the example. Okay, before I go to the example, they said acceleration is change in velocity. Sorry. Acceleration is change in velocity with time. So that's the same thing as saying delta V all over delta T, where it's the final velocity minus the initial velocity all over the final time minus the initial time. Guys, acceleration can be written as A equals to VF minus VI divided by TF minus TI. So that's the formula for acceleration, and it's measured in meters per second square. Meters per second square. His younger brother is just measured in meters per second. They don't usually give him 2 meters. The eldest brother, acceleration, they give him 2 meters, that's second square. The younger brother, they don't give him 2 meters, just second. Then the one that is below, they don't even give him meter at all. That's S. S is representing, I'm trying to use S to represent the meter. The eldest brother, acceleration, has 2 meters, as meters per 2 meters. And the other guy, velocity and the speed, they give them meters per 1 meter. That's per second, just second. Then for displacement, they don't even give it meter at all. It's just meter, just measured in meter. Then position does not even have a measurement. It's just a point. So they don't give that one food at all. The wicked family. So this is the example. This is the example to just try a simple example to try solving acceleration. It says a car increases its velocity from 10 meters per second to 30 meters per second in 5 seconds. So they said in 5 seconds. Sometimes you might be reasoning which one is the final time and which one is the initial time. So now they're already telling you in 5 seconds that they've already done the difference between the starting time and the ending time. So between the starting time and the ending time was a change of 5 seconds. So you might see it like that, where they will not tell you final time and initial time. They just tell you in 5 seconds or between 5 seconds or within 5 seconds. You would know that they've already gotten the change in time. Sorry. So, but in this case now, they've not given us the change in velocity. So sorry. Sorry about that. So the formula is just to divide or subtract first the velocities, final minus initial, then divide it by the change in time. That's what we can see here, 30 minus 10. This is the initial time, the initial velocity. This is the final velocity. So final minus initial, 30 minus 10. divided by 5, and that will be giving us 4 meters per second. So that's actually how we calculate acceleration on the basic level. So this is how we calculate both displacement, velocity, and acceleration on basic level. So moving on to advanced or a little bit more advanced ways of calculating these same parameters. So I'm supposed to give an example where we have to solve this, but I think it should be basic. Just if you can hear me, I would like you to just give me the answer for this. I'd like someone to just give me the answer for this question.
The answer is 2.
Okay,
2
okay,
meter per
very
second.
correct. Yeah, 2 meters per second or 2 meters per second square.
2 meter per second square.
Oh, thank you. 2 meters per second square. So because they're asking for the acceleration, so acceleration is their most senior brother, so they give him 2 meters, so that's second square. So velocity is what we are given. They gave us two velocities, the initial and the final. So the initial minus final is 8. Sorry, the final minus initial is 8 minus 2. And 8 minus 2 is giving us 6. So divided by 3, 6 divided by 3 will be giving us 2. That's how we are supposed to, that's how we could get our acceleration from this question. So let's move on to the next phase of this lesson. Graphs and graphs of motion. So graphs of motion, as we know that we talked about velocity, we talked about displacement, we talked about acceleration. They also have graphical representation that could also represent this elder brother, younger brother, and most senior brother. So we'll be trying to see how um, graphs can be used to represent these things. So let's move on. So for graphs of motion, we have basically three types of graphs for motion. For basic motion, I would say it that way. So we have a distance time graph or displacement time graph. I said they could be used interchangeably because they are twin. So distance time graph or displacement time graph, velocity time graph, or speed time graph. Then we also have acceleration time graph. You get, so these different combination of graph. So when you hear something like distance time graph, usually the first one they mention is always representing what is on the y-axis. Then the second one is always representing what's on the x-axis. So in this kind of graph, distance time graph, the distance is on the y-axis, time is on the x-axis. Every time you see, even if um, they say, let me use a name. They say a Buhari Tinubu graph. It means Buhari would be on the y-axis and Tinubu will be on the x-axis. So the one they call first is always the one on the y-axis, and the one they call next is the one on the x-axis. So that's how they put it. So when they say a distance time graph, it means there's a graph where you plot distance on the y-axis and you plot time on the x-axis. In the velocity, you apply the same thing. Velocity on the y-axis, time on the x-axis. Then acceleration on the y-axis, time on the x-axis. So the similarity between these three types of graph is that all three, time is always on the y-axis. It's always on the x-axis, sorry. Always on the x-axis. So as I said each graph tells a different story about motion. So we'll see how these graphs can tell story, or this kind of story that these graphs tell. Move on to the next slide. So for a distance time graph, when it's, I would show you in picture form, but for now, I'll just try to explain it. When you see a straight horizontal line, it indicates constant speed. Constant speed. A straight horizontal line indicates constant speed. We'll see it in the image. Let me even switch up. So if you can see this point that they pointed this arrow saying stationary, it indicates constant speed. It can, in place of this stationary, it can be replaced with constant speed. Constant speed or stationary speed or not changing speed. So at this, when they try to tell you that the speed of a body does not change between as time changes, if you want to represent it on a graph, it will be a horizontal line because the velocity or the distance is not change with time. Distance, they're trying to tell that if the distance on the y-axis here, distance here, it is not changing, it means that this value here, as you keep on moving with time, it is remaining constant, remaining constant, remaining constant, remaining constant because it's not changing. So it's stationary speed. When you see a horizontal line like this, it's depicting stationary speed or constant speed. You guess, because that's for a distance time graph. When you go back a bit. When you talk about a distance time graph, usually what is depicting is always telling a story of speed. It's distance time. Remember that distance over time is used to measure velocity or speed. Distance over time or displacement over time is used to measure velocity or speed. So when you're interpreting a distance time graph, you are usually interpreting it with respect to speed. So it's talking about constant speed. Now let's move on to the slide, to the picture again. So when you see it is continuously changing upward. It means it is moving uniform speed. That is, as time is increasing, the speed is also increasing. And this kind of movement where speed is increasing with time is known as acceleration. It's known as acceleration, but this they call it uniform speed. Later you understand why I say it's known as acceleration. So this is used to represent uniform speed on a distance time graph. This kind of line, a slanted line moving from left to the right, moving upward from left to right on a distance time graph is known as uniform speed. But when the line is horizontal, continuously moving from left to right, it's called constant speed. So you can see this was a uniform speed. This was another uniform speed. Another uniform speed. Then when you start coming down now, it's what you call negative speed, or if it were to be in a velocity time graph, it would be called a deceleration. So here what's happening is that as time is changing, your speed is reducing, or the person's speed is dropping as the person is moving, as time is going by. Because this line moving like this means that time is changing. So as time is changing, the person was increasing his speed, then maintained a constant speed, then increase again, then started slowing down as time was going. So that's the story that this graph of distance time is telling. It's telling how this motion took place, how the speed. We can look at this and say, okay, we already know that anytime we see slanted line moving from bottom to top, from left to right, when we see a slanted line moving from left to right, upward, when we see that kind of movement, it's a uniform speed. So when we see it horizontally moving, it's a stationary or constant speed. And when it's moving downwards, it's known as a slowing speed, or I can call it a negative speed, because it's a deceleration sort of. So we can tell the story that, okay, as when it was a boy or someone's movement you're trying to represent with this graph, you say the person was increasing his speed from 1 to, in 1 second, he increased by 1. In 2 seconds, he increased by 2. Sorry. In 3 seconds, he increased by 3. Then in the 4th second, he did not increase again. His speed was the same, 3. In the 5th second, the speed was the same, 3. In the 6th second, the speed was the same, 3. In the 7th second, the speed was the same, 3. Then once thing reached like that, in the 8th second, the speed increased 3 times. This is 3, this 4, 5, 6, increased to 6 within 1 second. So you see the speed. That they said is fast uniform speed, because thing was very steep rather. It was very much almost like a straight line upwards. So this thing can tell you that within 1 second, this person changed speed from 3 to 6. So it's indicating that this place, it was a fast movement here. Then over the space of 1, 2, 3, 4, 5. By the space of 5 seconds, it took the person to slow down and come back to rest. So when it is at this bottom line, it means the body is at rest. It's not moving at all. That's the story that a distance time graph can tell. I don't know if anyone has a question about this I just explained before we move forward. I would like you to just ask a question. If you have your question, just ask me. No question. Okay. So it's good. So we are good to go forward. Let's move on to this is the story that a distance time graph tells us. Now let's move forward onto a velocity time graph. So it's similar to a distance time graph. The terms, they are very similar, but not exactly the same. So for this one, the horizontal line tells constant velocity, constant velocity, constant velocity. Then what they call it, a slanted line, if it's slanting from down upwards, it's known as acceleration. While if it's slanting from up downward, it's known as deceleration. So the area that is usually under this graph, under this kind of graph, is known as displacement. Known as displacement. So let's see what it looks like. So this is it. This is a speed time graph. It's a speed time graph where speed is on the y-axis and time is on the x-axis. So it could be called a velocity time graph also. So what this means is at this point, the speed was zero. As I said, when you are on this horizontal level, even if time is changing and you are still on this horizontal level, it's telling that there was no change in speed. The speed was the same, was zero cell. Because it has not gone above zero. This is we assume this point on zero. So the speed has still remained at zero. Then the story is telling that at some point in time, it started increasing constantly increasing. So this phase of constant increase is known as acceleration. When you see a slanted line like this, known as the acceleration portion. Then when you see constant movement, is known as constant speed. When it's moving like this, it is constant speed. When it's just horizontal, it's constant speed. And when it's moving downward, it's constant deceleration. Constant deceleration, that is slowing down, almost the same as the story of distance time graph tells. It's just that in case of speed time graph or displacement or velocity time graph, you don't call it just you don't call it the same things you call those ones here. Yeah, we call this one uniform speed. But in case of this one, we call it constant acceleration or uniform acceleration. Or preferably constant acceleration. So it's accelerating constantly. Then it then maintains a constant speed. It starts decelerating. That's the story that a speed time graph tells. However, for an acceleration time graph now, they all look similar. They have similar um explanation. They are similar sort of. So for this acceleration time graph, we have straight line also represents constant acceleration. Constant acceleration. Then the line under the graph of this is known as velocity. So looking at this thing, I said the area under the graph for an acceleration time graph is called the velocity. Just like I was asking you, the younger brother, that's the area under this, under an acceleration time graph, the area that is under the graph is always known as the change in velocity. While for this one now, for speed, the area under this graph, the area under this graph is known as displacement, as I stated here. Known as displacement. That's the younger brother of velocity. That's displacement. While on this other one, we didn't really state it, but we didn't really state what this one is. Or I've not really heard of what it means. But usually it's from this point that they begin to mention what these areas mean. But the area is supposed to mean maybe position for this first one. But I can't just say that. Let's just move on to this. Move on to acceleration that we were talking about, acceleration time graph. So constant acceleration, as you can see here, is still represented with a horizontal line. Horizontal line, constant acceleration. So then we also have uniform increasing acceleration is represented with this. Increasing acceleration is represented like with this. While on uniform acceleration, it bends, is either bends this way or bends the other way. Like the curve is either curving like this or curving upwards. You get, so that one is showing that it's not uniform. When it's non-uniform, it is not changing equally with time. So how is it uniform? On this one, if you move up this distance, that same movement is what you take this distance. If you move up this distance, that same distance will be almost the same thing when you measure it on this side. This distance will always be almost the same on this side for uniform. But for non-uniform, you move up here just small, but see how far you've moved on this y-axis. You move just small on the x-axis, but see how far you've moved on the y. Sorry, move small on the y-axis, but see how far you've moved on the x-axis. And when you keep on moving higher on the y-axis, you've just gone just this distance on the x-axis. So it's not uniform. That's what I mean by non-uniform acceleration. So that's what the story that these graphs tell us. These graphs they tell us these stories. Let's move on to the next. Let's move on to the next straight up. We have free fall. Free fall. So when we talk about free fall, we are talking about dropping a body under the influence of gravity, or leaving a body that is under the influence of gravity and gravity alone. So if probably you say something is dropping, then maybe something is, as it is falling, something is placed on top of it. It's not just under the influence of gravity alone. Probably there's an extra force that's acted upon it, and you cannot call that in a free force or a free fall. Sorry. If it was shot downward or it was thrown downwards with force, it is not allowed to fall freely. It's not called free fall. So, but when something is made to just drop on its own without any extra force adding it, just letting gravity be the one that will take it downward, this is known as free fall. Free fall, when you allow a body to just drop on its own accord or vertically from up downwards, is known as free fall. So free fall cannot be from down upwards because it's a fall. So it's always movement from up downwards without the influence of any external force, just gravity alone. Just gravity alone. So here we have key points. When we talk about free fall, when an object is said to have free fall, the acceleration is usually said to be 9.8 or 10 meters per second square. So it's usually said to be this. And in real sense, there is actually nothing like free fall per se in logical sense, nothing like free fall, because no matter how something is trying to be said to be, is said to be falling freely, air always affects it. Like air is always, there's always something like air resistance. If something is falling downwards, the air that is trying to tear through will be slowing its speed in a way downwards. It might not be significant, but there's a form of resistance. So that's why they said things are not necessarily, you cannot really say something is falling freely completely, but the resistance when something is made to fall freely is actually negligible because almost significant to nothing. Almost significant to nothing. So long as the thing is falling from a particular, so long as it's dropping, it's what they call it, it's air resistance is negligible. So now let's go to equations of motion, or what they call equations of free fall. These are common equations that most of us know. And I believe that anyone that studies physics or that has been doing physics should be able to call these equations off their head without looking at any paper, or it should sometimes you should have already at the back of your mind, whether you're woken up from a sleep or something, wherever you find yourself, you should be able to call this without thinking twice. The three equations of motion or equations of free fall. So the first one is written as V equals to U plus AT. So in case you've not memorized these formulas, I would advise that if it's possible, every early morning you wake up, recite the three of them. They are simple, they are very short. They are simple, they are very short. Just S is equal to UT plus half AT square, V is equal to U plus AT, V square is equal to U square plus 2AS. This you're supposed to be able to say at the back of, like, without even looking. So these equations are very important when you talk about basic physics or classical physics. So these equations are the starting points. to memorize these formulas because when you go to usually these are the basics of most physics calculation questions. Based on most physics calculation questions, they would always give you questions where you need to find one of these parameters and you need to choose between either of these three equations. So the meaning of these parameters now, we have V from this, we can see V, we can see U, we can see A, we can see T, we can see S. So that's what we have here, V, U, A, S, T. So each of these, V represents final velocity, U represents initial velocity, A represents acceleration, while in some cases, when you talk about free fall, they would replace A with G as acceleration distance. And S is known as distance or displacement. Distance or displacement. Then we have T representing usual time. Let's an example. An example is that an object falls freely from rest. Find its speed after 4 seconds. An object falls freely from rest. Find its speed after 4 seconds. So first off, we already know that it's a free fall equation. So meaning that wherever we see our A, we would always replace A with G. We said our G is 9.8 or 10, usually 9.8. So now, to solve this kind of question now, you take time. What did they give you? They gave you just time set from rest. So this statement from rest is a very crucial statement from rest. Something falls from rest. It's very important that you take records of it wherever you find it in a sentence, because once you see in a question they said something moves from rest, they are trying to tell you already that the initial velocity is zero. If they say something comes to rest, it means that the final velocity is zero. When they say it starts from rest, the initial velocity is zero. But when it says it goes to rest, you get when it goes to rest, the final velocity, that's v, in that case, zero. So it's important that you pay attention to these things I just said now, because it could help in solving questions. It will help in giving you ideas for solving questions. It will help you giving parameters for questions. So now from this question now, we are seeing that they said an object falls from rest, meaning that they mentioned our
Yes,
u.
please,
Yeah,
can
I'm listening.
you yes, can you repeat what you have just said? That if it starts from rest, the initial velocity is what?
Okay, when you hear that it starts from rest, it means that u is equal to zero. U is being the initial velocity. So the initial velocity is zero once it starts from rest. Starts from rest, or anyhow that you're trying to say that begins from rest, starts from rest, or was thrown from rest, or was dropped from rest. So long as it's starting, the initial point is rest, it means that the initial velocity is zero. So when you then talk about it comes to rest, as it means that there's something ending final motion, and then relaxing, that is stopping. So at that kind of case now, the final velocity is said to be zero, not the initial at that case now. So now the initial is only zero when they say it starts from rest. The final is zero when they say it ends at rest or it comes to rest. Usually you see it comes to rest or ends at rest, or starting on it will be starts from rest or begins from rest. So you get that's just it's weak. So it's important that you pay attention to this structure of sentence so you will not make mistake. Because in this question, you might just be seeing an object falls free from rest, find its speed after 4 seconds. You'll be like, and they gave us only time. They gave us only time. Actually, they gave you time and the initial speed because it said it falls freely from rest. And also, aside them giving you initial velocity, they also tell you it falls, meaning since it's a falling motion from rest, they've told you the acceleration at the same time. So another tricky sentence that you will see in most of this kind of question is they will say
Please,
it falls.
I'm not following. Please, sir.
Okay, sorry. So where would you like me to repeat myself from? Hello? Hello?
I said from after the equation of free fall, you are giving
Okay,
us when we see this, we know that is this. I'm confused there.
okay, okay. So let me take it one by one again. Probably if you want to write, you would write it down.
Yes, that the initial velocity is 0. Other ones I didn't get it.
Okay. When it starts from rest, the initial velocity u is equal to 0. When it starts from rest or when it begins from rest, the initial velocity u is equal to 0. So when they say the body comes to rest, or ends at rest, it's meaning that the final velocity is 0. When they say it comes to rest, usually you see that it comes to rest. Maybe they say a car was moving at so speed, then comes to rest after 5 seconds. They are telling you that the final velocity is 0. So when they say comes to rest, they're trying to tell you that the final velocity is 0. I don't know whether I'm clear.
Yes, yes.
Okay, so that's it. So another tricky sentence that they could use to mask some of the parameters is they could say something like it falls with gravity, or an object is thrown upwards, or an object falls. So when you hear that an object falls or an object is thrown upward, vertically upward, when they say something is thrown vertically upwards, just know that they are telling you that the acceleration as g is negative. So write it down. When they say an object is thrown vertically upwards, it tells that the acceleration is g,
Please mute yourself.
and the
Your
g
mic
equals.
mute yourself.
You say my mic is cracking. Let me repeat myself.
I mean my fellow students. Let them mute themselves now
Okay,
so that I can hear you very clearly.
okay. Sorry, please. I don't know whose mic was turned on. Just please do us a favor and help us turn it down so that at least we would be able to hear ourselves. So as I was saying, another tricky sentence that you could see in all this kind of question is you would see that a body is thrown, I mean something is thrown or something moves vertically upwards. So first case, vertically upwards or upwards, whether they say vertically upwards or they just say upwards, is already telling you that the acceleration, which is your g, which is becoming your acceleration due to gravity, is minus 10 or 9.8. When you see vertically upward, automatically they're trying to tell you that acceleration or g is equals to 10, that is equal to minus 10 or minus 9.8. So this is one of the tricks you will see in some question. You will just see something is thrown vertically upwards. You will not know that actually they are already giving you an hint with that sentence. So now the other side of this sentence is when they say something falls vertically or something falls downwards. When they say something falls downward or something falls freely or something falls from a height, so long as you're hearing the sentence falls, that is falling down, like falling down, they're already telling you that the acceleration, which is the g, that is, which is your g, is equal to 10 or 10 or 9.8. So when it's falling, it's just 10 or 9.8. But when it's thrown upwards or moving upwards, it is what they call it. It is usually minus 10. Usually minus 10. That's usually the acceleration, minus 10 or minus 9.8 when it's moving upwards. When it's moving downwards, it is 10 or 10 or 9.8. So with these two cases of sentences, with these two cases or sentences, I believe we'll be able to decipher this question and know all the parameters we're given in this question. So from this question now, we'll be analyzing this question sentence one by one. They said an object falls. We already seen one of our case sentence, falls freely, meaning that we'll look at our case where we talk about fall. When we are talking about fall, it means that they are telling us that our acceleration or our G is equal to 10 or 9.8. So we'll write that one down as 1 point. That's what we can see at this point here. Acceleration or G is equal to 9.8. Now we are seeing here, acceleration or G is equal to 9.8. So because of these falls that they mentioned here, that's why we can tell this. So now, when they now said it falls freely from rest, so it means they're saying it started from rest, So we are now going to our second case of sentence, which says from rest means that our U is automatically 0. So that's what we can see here. Our U here is automatically 0. So we've written our U and we've gotten our A and G, that's A or G. Then now the next parameter, they now said find its speed. So if they have already told us that the beginning speed, which is our U, is equal to 0, meaning that any other speed that they're trying to ask you to find is your final speed. That is your V. They're asking you to find your V. So and they said after 10 seconds, that is time is 4 seconds. So when you write all these parameters that you are given from the question, you then look at which of these formulas, which of these our equations of free fall, which of them has all the parameters that we are given. So this one now, this equation has S, but from what they gave us here, nothing has to do with S. We are looking for V, we have U, we have A, and we have T. Nothing that they gave us is relating to S. So meaning that this formula is cancelled out because nothing is relating to S that they mentioned to us. So here now, we are giving V, we are looking for V. Yes, this one is part. We are giving U, and U is in this formula, that is good. We are giving A is in this formula, that is good. But now S was not mentioned again. So we don't need any equation that has S inside because we have nothing to do with S. They did not mention anything about distance. S is representing distance or displacement. So now, this is the only formula that has all we have, all we are given. We are looking for our V, the final speed. We are giving U, the initial speed. We are giving A, which is our acceleration due to gravity, and we're also giving time. So meaning automatically, this is the formula we just use. So once you've known the formula you use, you just plug in every single thing you were given, where they are. So our U is 0, our A is 9.8, our T is 4. So you put it in the formula, V will be equal to 0 plus 9.8 times 4. And if you press your calculator, you'll be having 39.2 meters per second. So that's how we solve questions like this. It's not really much of a big deal. It's just for you to be able to understand those case sentences that I mentioned, where they will tell you from rest, or it's thrown upwards, or it's dropped downward. Those kinds of sentences, they are the sentences that can make this type of question tricky. So once you've gotten the hang of those sentences and you check a question and you find them inside, you'll be able to know what you are given. Then the obvious ones, you then write them out as well. Then you go to your equations of free fall and check which of these ones would add well to the parameters that we have already. So now let's go to our next slide. So our next slide is now projectile. So I know projectile is a common topic that we meet in secondary school, SS1. I'm correct. Usually a topic that we see in SS1, one of the first topics. So the same with JUPEB, it's usually one of the early topics. So projectile is actually a form of motion. But now, when you say, if you remember when I was talking about translational motion, it's a movement in one direction, like moving like this, the translational motion. So now, when this translational motion now is going somehow along a curved path, something like that, when it's moving along a curved path, but it's still moving forward, it's not going like this and coming back again. It's not moving in circle, sorry. It's not moving in circle, but or it says a rotational motion. It's not moving like this, or it says a vibrational motion. It's moving just like this from one starting point to an ending point. It's a transitional motion. But now this kind of transitional motion is called a projectile motion, where the motion of the transitional body is moving in a curved path. It's moving in a curved path. It's moving in a curved path, or also known as a parabolic path. So when you talk about projectile, you would always talk about curved motion. Curved motion. You'd always talk about curved motion. Usually the kind of thing that you see when you kick a ball, it will move up and a particular speed, move up, then to get to a point, start coming down. That's a kind of, so long as it is leaving the ground or leaving its base level where it started from and moving, tracing a curved path on the air, it's a projectile motion. Even when you throw stone, it's a projectile motion. So this curved motion, where you see something moving in a curved path, is known as projectile motions. So the key points in projectile motions is that there is always what we call the horizontal and vertical motion. So in that curved path, there's always a point where the object is moving upwards, though not straight upwards. It's moving upwards. So this is the vertical movement. Then downward, it's still the vertical movement. But at the same time, as it's moving upwards and downwards, carrying out vertical, what they call it, vertical movement, it's also moving forward. That's also a form of horizontal movement. So projectile motions always move horizontally and vertically. They always cover a vertical part and also a horizontal part. When I go to the image, I believe I'll be able to explain this clearer. So then we have horizontal velocity. In projectile motion, it's always assumed in projectile motion that the horizontal velocity.
Explain the projectile motion again, please.
Okay. Projectile motion is a kind of motion that moves along a curved path. It's a kind of translational motion that moves along a curved path. So if it is just moving in a straight line, you cannot call it a projectile motion. If it's just moving in a straight line, you cannot call it a projectile motion. It's a normal transitional motion. But when it's now a transitional motion, what makes a motion a transitional motion is when it has a starting point and it moves forward or backward to another point without returning back to its initial point. It's a transitional motion. So now, what now makes a transitional motion a projectile motion is when, as it's moving from one point to another point, it is moving in a curved path. When it moves in a curved path, that transitional motion is not just an ordinary transitional motion, it's a projectile motion or a projectile transitional motion. I believe that is clear. So now, as I said, all projectile motion always have horizontal motion and vertical motion. All projectile motion, they always have horizontal motion and vertical motion. So meaning that assuming you threw this thing, see from this my pointer, it moves upwards, then start coming down. It covered a horizontal distance. It moved like this, then came down. There was an horizontal movement I think covered. Then at the same time, as it moved like this, there was also a vertical movement covered. So projectile motion always have vertical motion and horizontal motion. This is the characteristics of projectile motion. They always have vertical motion and horizontal motion. So now, another key characteristics of projectile motion is that the horizontal velocity now is always assumed to be constant. The horizontal velocity is always assumed to be constant. For projectile motion, the horizontal velocity is always assumed to be constant. While the vertical velocity, that is the velocity that is moving upward, is said to change with time. It changes due to gravity. So these are characteristics of projectile motion. The first one is that it always have horizontal motion, vertical motion. The second one is that the horizontal velocity is always assumed to be constant throughout the motion, while the vertical velocity is said to change during the motion. And this change is because of the effect of gravity, because as things is moving upwards, gravity will be obstructing it. And even as it's coming down, gravity will be influencing it also to come down. So that's one of the key points or characteristics of projectile motion. Let's move on to the image of what it's looking like. So this is what a projectile motion looks like. It's always a starting point where you shoot something off with a particular initial velocity. That's an initial velocity. That velocity keeps on moving, keeps on moving. As it's moving upwards, to get to a point when it stops, then starts coming down. You've observed when maybe you throw your key upwards to the air, or throw your key towards someone, it goes up, it keeps on going up to a point. Then at a point, something just happens, it starts coming down. So what happens is that the initial force or velocity used to send it upwards was reducing because gravity is a force that's acting downward. So as thing is moving upward, gravity is reducing that velocity because gravity is trying to send it go down, go down, go down, go down, go down, go down. As it's going up, gravity is telling it go down, go down, go down. Then it gets to a point where gravity will overcome it and it will be like, I don't tire. Gravity is wasting all my strength I'm supposed to use to run upwards. So gravity will waste its strength and it become zero at that maximum point where it gets to. That point when the initial velocity becomes zero. That point when the initial velocity or when the initial velocity becomes zero is known as the maximum height. It's known as the maximum height. The point when the initial velocity is zero is known as the maximum height. Because when it has become zero, the next thing that happens is not going to go upward again. It starts coming down. So it has gotten to its highest peak. Or it has gotten to its peak. Let me not speak in tautology. So it has gotten to its peak. The highest and peak, they are interchangeable words. So I don't want to, it's not proper to use highest and peak because peak is always representing highest. And so it's tautology saying highest peak. It has gone to its peak or to its highest point. And that highest point is marked as the maximum height. So then after that point, to start coming down, coming down, coming down, coming down. So this is clearly the path of a projectile motion. And now there is what they call the range, which is the distance between the starting point where you threw your key to where the key landed. That distance between where you threw your key and where the key landed is known as the range. That's the horizontal motion. The distance covered horizontally is known as the range. Distance covered horizontally is known as the range.
From here to where, sir?
Yeah. From where you started throwing the key from.
The initial velocity.
Okay. The initial velocity is when you started throwing the energy you used to throw it upward. There is always a velocity that comes with that energy. So that velocity will keep on increasing. It will keep on decreasing as you throw something upwards. It will keep on reducing to a point when it has used up all its velocity, it will become zero. So that point when this velocity becomes zero is known as the maximum height. It's known as the maximum height. When the initial velocity becomes zero is known as the maximum height. The point when the initial velocity becomes zero is known as the maximum height. Then that initial velocity will then start, it will then start dropping downwards. Gravity will start increasing it, giving it another velocity again downward. So it will start falling downward across a path. So that's for the horizontal movement to keep on moving up, get to a maximum point, and start coming down. That point is the maximum height. Then when you're talking about the horizontal motion now, where you started from, where it was thrown, where that body was, where that key was thrown from, to where the key landed. The distance between where it was thrown from to where it landed is known as the range. That horizontal distance between where the key was thrown from and where it landed is known as the range. The same as where you throw stone, when you are throwing stone, when you are throwing the stone upwards or upward and forward. When you throw the full stone, your point where you started, where you stood to throw the stone, where the stone landed on the floor. The distance between where you stood to throw the stone and where the stone landed is known as the range. It's known as the range. So that's for that. Then the total time that it took for the stone to move up then come down and reach the ground. The total time that it took for it to complete this whole movement is what they call the time of flight. It's called the time of flight. The total time it took for the object in projectile motion to move from its starting point to its ending point is known as the total time of flight. The total time of flight is the time it took for it to start from its starting point to its ending point. That's known as the total time of flight. So there are formulas for these three things I just mentioned. I mentioned maximum height, I mentioned range, and I also mentioned time of flight. Time of flight, maximum height, and range. Now this is a simple definition of or this is a simple diagram showing what projectile motion looks like. So this one here, where the guy threw it forward until it landed downward. This is an example of a projectile motion. Typical example of a projectile motion. So in this kind of case where he threw it just upwards and it came downwards, it's a form of projectile motion, but not a perfect projectile motion, because just like I said, it's an upward motion and a downward motion. So it's not really a projectile motion per se, except when where the ball was at the beginning is different from where it was at the end. Even if you threw it upwards, and it's like you threw something upwards and things did not fall back on your hand. If it falls back on your hand, it's not a projectile motion. When you throw it upward and it does not fall on your hand back, that's taking a projectile path. So it can be considered as a projectile motion somehow, so long as the initial starting point is not the same as the ending landing point, and there's a curved path that was traced. Projectile motion. So another type is dropping an object from up downwards. When you just drop it from up downwards, that's not really a projectile motion, it's just a free fall motion. But when, assuming you are standing somewhere and you just threw it forward a bit and the thing went forward and fell down, created a curved path, it's a form of projectile motion. So now, the formulas that I told you, I said we had time of flight or total time of flight. We had maximum height, and we have range or horizontal range. These are their formula here. Time of flight. The formula for time of flight is 2u sine theta over g. So if you see here, they wrote v naught, that is v0. Here they said 2v0 sine theta over g. So in case you see v0, v0 is trying to say the same thing as initial velocity. So you can see it as v. Yeah, you said what? Sorry, someone said something. Okay, I think no one said something. So when you see V naught or V0, it can be used interchangeably for U, because V0 means this velocity at zero, that is the starting velocity, which is the same as initial velocity. So V0 is initial velocity or U. So the formula can be written as 2U sine theta over G. It's always the same for total time of flight. So sometimes they might tell you that it's not total time of flight, tell you time of flight to reach the maximum height. When they tell you time to reach the maximum height, at that case now, these two would not be there. These two V naught sine theta over G. These two will not be there. They say it's time of flight to reach maximum height. The two will no longer be there. So when they say it's time of flight to reach maximum height, the two will not be there. But when they say normal time of flight or total time of flight, the formula will be 2v naught sine theta over g, or 2u sine theta over g. So then for maximum height h, the formula is v squared or u squared. I'll prefer using u squared instead of v naught. So u squared sine squared theta. U squared sine squared theta over 2g over 2g. That's the formula for maximum height. While for horizontal range, the formula is v squared or u squared. I said I'll be using u squared sine 2 theta over g. U squared sine 2 theta over G. U squared sine 2 theta over G. So there is something that is unique about this range. There's something that is unique about this range, or is important to take note, because it's a form of question that always come out. They'll say, what angle would give the maximum range? What angle of projection? Because when you're throwing something like this, there's always an angle, like the thing is moving towards. There's an angle. When you throw something forward in a projectile form, there's always an angle that is there. So when you throw this thing, that angle, they're not asking that what angle. They can ask a question like, what angle would give you the maximum distance, that is the maximum range. So the angle that's always is something. This one is a constant. So just write it somewhere in your notes. The angle that would always give the maximum range. The angle that would always give the maximum range is angle 45. The angle that would always give the maximum range is angle 45. That is 45 degrees. 45 degrees would always give you the maximum range. 45 degrees will always give you the maximum range. So now, the trick I use to memorize these three formulas is this. I always arrange them as time of flight, range, then maximum height. Instead of like this, I always put time of flight, range, then maximum height. That is TRM or something like that, or TRH. TRH. Time of flight, range, then maximum height. Time of flight, range, and maximum height. So then how I do is that I'll say, in time of flight, everything has U sine theta over G. All of them has U sine theta over G, U sine theta over G, U sine theta over G. But now, these two that is behind them is always shifting. So from T, in the one of T, the 2 is with the U. In the one of H, the 2 is with the theta. In the one of G, the 2 is with the G. So in the one of H, the 2 is with the G. So if you cannot memorize it straight up, you could just use the TRH arrangement. Then you know that for the first one, 2 will be in the U. The second one, the 2 will shift to the theta. The next one, the 2 will shift down to the G. So that is how the movement is. Movement is like that. Then you now start saying when the 2 is down, when the 2 is on G, square will be on both of them. When the 2 is on theta, square will be on only the V. But when the 2 is on V, none of them would have square. So it's just a way that I use them to memorize it. So you could form your own, or you could actually learn it by inculcation. Just continuously be repeating it in your mind or in your head, or writing it almost every time repeatedly. When you keep on writing it repeatedly or saying it outwards repeatedly with your mouth, saying time of flight is equal to 2U sine theta over G. Time of flight is equal to 2U sine theta over G. This was a method that they taught in primary school, how they teach children when they were small. They teach children by inculcation, where you would repeatedly say something over and over and over and over and over again. That even if they don't want to learn it by themselves, their brain, because of that repetition, would study that recurrence, that once you start or you mention one, your brain will help you complete the rest. So this is one way that you could help to improve your own learning pattern, by inculcation, repeating something over and over and over again. That is why most of us, was difficult for us to learn to forget ABC. A for apple, B for ball, C for car, or A, B, C, D, E, F, G. You know how many times we recited that thing when we were in primary school? Every morning you come, you recite it. In the afternoon, you recite it. And before you go home, you recite it. So this continuous repeating pattern, it helps to make some kind of all this type of things that are constant in a direction. It helps us to memorize them easily. So you could keep on rewriting this formula or resaying the formula. When you keep on resaying the formula over and over and over again, you find out that you memorize it. So without spending much time here, let's go to an example here. So in this example, they said,
I have question there.
so,
That time of flight. Yes, that time of flight. You said that. You said that there's something you said that
Okay.
I didn't
Okay.
get you.
I said in time of flight, there are two ways that they will mention time of flight. They will say time of flight normally or total time of flight. The real thing is time of flight or total time of flight. That is the normal formula for this. That is the normal one that has this formula. 2u sin theta over g. But when you now hear time of flight to reach maximum height, when they say time of flight to reach maximum height, time of flight to reach maximum height, you would now know that instead of putting this 2u sin theta over g, it will now be just u. That 2 will disappear completely on the time of flight formula. It will be the same formula, but the 2 will disappear completely because they are talking about the time to take to reach maximum height. So let me explain why it's like that. This is the time, there's a time that you take it to move to this maximum height. And that same time used to reach this distance. So when you talk about the total time of flight, it's adding distance added is went like this, and the distance is went like this. So when they now talk about just the time to take to reach the maximum height, it is the total time divided by 2. So because it's divided by 2, that's why that 2 will be removed. I don't know whether
Okay.
I'm communicating.
Yes, or the 2 is removed entirely now because it has
Yeah,
to
the 2
be.
is removed.
It has to be at the middle. The time has to be from starting point to the middle.
Yes, yes. So instead of you to calculate the full time of flight, that is total time of flight, that is 2u sin theta over g. Now you'll be calculating half of it. So now that 2 will away.
Okay, it's well understood. Thanks.
Yeah, thank you. So now let's go to an example. Horizontal projectile. So the question says a ball is thrown horizontally. Then a ball is thrown. My time is up. Well, let's see how many slides are there. Okay, we're almost done. Thank God. So they said a ball is thrown horizontally from the top of a building, 4 meters high, with a velocity of 8 meters per second. How long does it take? Does it take the ball to reach the ground? And how far from the base of the building does it land? So this question is actually very tricky. Actually very tricky. What they're trying to say is something like this now. Trying to say that let's assume something is someone is on top of a building and he threw a ball from that building up and the ball then came down and reached the ground. They're not asking you that the person will say, how long does it take the ball to reach the ground? They're not asking you for the time it takes to reach the ground. So it's important that we should notice something. Normal projectile motion always looking like this. It's only this top part. These are normal projectile motion usually look like. So now, but there's now an extra distance. Sorry. There's now an extra distance that happens downwards that we would also need to take account of. So normal projectile motion is just like this, like this. But now there's an extra movement that comes downward. So because of that, they ask us to find the time it takes to reach the ground. So meaning that we'll first find the total time it takes to go like this. Then we'll then use our normal equation of free fall to check the time it moves from here to down. Then once we've gotten that time, and be able to add it together. But there's actually a simple formula to calculate it. There's actually a simple formula to calculate it.
Check it again.
You said I should repeat it again.
Yes.
Okay. So I said normally the normal projectile motion is always moving like this. Go up, then come down. This is the normal projectile motion looks like. But now, when you then are changing from normal projectile motion now in this kind of scenario, this kind of question where they mention that you're standing on a building, the building already has its own height. So after the thing has moved through the projectile motion part, to then move another direction downwards again. So it will move like this at a particular time, then move like this downwards with another time. So to get the total time, it will be taking the total time that thing will travel to reach the ground. We will measure the time it went like this. and also the time it came downward. So it's a combination of both projectile and normal free fall. The combination of projectile and normal free fall. Or we could divide it like this, saying that it moved upward, then it fell freely downwards. Let me clean this up a bit. This is the view. Then it was thrown upwards, or it was thrown like this. Sorry. It was thrown like this. Then when it got to the same level, it then started falling down. So you can divide this motion into two, saying like this, dividing it into two, where you use normal projectile to get the movement like this. Then this other one here, you use normal equation of motion, free fall, to get this side. So that's what we'll be trying to do. But there's a simple formula. There's a simple formula, and there are actually some formula that they use for this kind of stuff. There's a formula that they use for it. So the formula for this kind of question, when a ball is thrown, I would like people to write this one down, so it will not stress. It will not stress us to calculate using the other pattern, because that one is it's a bit complex and it saves stress. It's more tasking. So instead of trying to go through that long pattern, just go to the alternative formula. So the thing you should just recognize is when you are given a question and they say it is thrown from a building top, horizontally from a building top. When it is thrown horizontally from a building top, the total time of flight is going to have the formula T. Let me clean this up. Sorry. When it is thrown from a building top, total time of flight is going to have the formula T equals to T equals 2s over g root. So this is the formula for what they call it. This is the formula for time of flight. When you are standing, when they say the object or the object was thrown horizontally from a particular height, either from a building top or from the top of a pole, or from just when they mention that something is standing from a particular height and throws an object horizontally. To get the total time of flight, this is what the formula is. T would be equals to square root of 2s over g. So that's what the formula is. So write it down, because that's what we're using to solve this question.
Where
So now,
S is
the
S,
said,
is it displacement or distance?
yeah, displacement and distance, we use them interchangeably. So it can be displacement, it can be distance. So long as it's measured in meter, that's supposed to be there. Something a distance measured in meter or a displacement measured in meter. That's what it is.
Okay.
Yeah. So now this formula for time of flight is used when they said it is thrown horizontally from a particular height. It's thrown horizontally from a particular height. That's when you use the formula for time of flight. Then the formula for range that you use for this formula, for this same case, formula for range that you use for this same case is the range is equal to U times T. The range is equal to U times T. That is the velocity times time.
Initial velocity.
Yeah, initial velocity times time. So these are the two formulas that they use for horizontal projectile. That is when they say something is standing from a building or standing from a particular height. It's only when they say it's standing from a particular height and it's thrown horizontally, that you use these two formulas I just gave. It's only when they say this that you use these two formulas. So once they say that, just know that the formula is this, and it's just plug and play. They either ask you to look for the range, or they ask you to look for the distance or the time it takes to reach the ground. That's exactly how the question appear like. And to solve that, these are the formulas you use. So if you use the first formula that I gave you, the first formula that I gave you, which is equal to square root of 2s over g. Our s in this question is 45. So we have roots 2 times 45 all over our g, acceleration due to gravity, usually 9.8. 9.8. So if you solve this, you're getting your t, getting to your final time to be. Final time will be giving you, you solve it correctly, your final time will be giving you 3.03. That will be the final answer.
Yes, sir.
That's what we have here.
3.03.
90.
So that's what we have.
Root of 90.
That's what we have there. So now, they now said in the second question, they said, in the B part of the question, they said, how far from the base of the building does it land? That's they're asking us indirectly for the range. Because they say, how far from where the thing started from would it land when it lands? So is the range. So I said range, according to what I was saying, I said, this is the building. Range is always the measure of starting points to the ending point. The distance, the horizontal distance is the range. So now they're asking us from the said, how far from the bottom of the building would it land? So now the range formula that I gave is just simple. I said R is equal to U times T. So this T that we're talking about, the total time of flight that we just calculated now, the T we just calculated. So now our U is what? Our U is 8 from the question. Our U is 8 from this question. And our T is what we just got, 3.03. So if we put it in the formula, we'll be having 8 times 3.3, 3.03, sorry. 8 times 3.03, it will be giving us our answer of 24.24. So the answer should be 24.24 if you calculate it. So the answer should be 24.24 if you calculate it.
Second.
Yeah, in meters. Because range is always measured in, it's measured of distance. So distance are always measured in meters.
The second cancels itself.
So that's this example. So I'm talking towards the end of this class, but before we get there, let's just there are some experiments that you will see on
Please,
under this stuff.
the last
slide.
Yeah, you should before this one. Please.
This one, is it this one? Okay, copy out.
I'm screenshotting it, please. Next one, sir. Next slide, please.
So now,
next slide.
We are now experiments now. So
Where
due to the fact that this is
where you wrote summary.
Yeah, no, this is the page before summary. This is the page before summary. So it's supposed to be experiment, but due to the fact that this is not, we don't have a lab here, there probably is a plan that maybe somehow would fit in, create a system that would help cover up for practical under these topics. Where practicals are necessary, we'll try so that we can create a system to attend to you guys in regards practical. For now, we've not really figured that out. But later on, we figure out something before this whole period of um, night classes is over. We figure out a way to handle practical for you guys. Hopefully, we find a way to handle practical for you guys. So that's for experiments. Then now, in summary, we've treated so far. We've been able to treat the types of motion where I talked about translational motion, being in motion, moving from one point to another without reversing or going backwards, just in a particular direction, forward or backward or any way, just a single directional motion. That is a linear motion. That's for one of the types. We also have random motion or Brownian motion, random motion, where it's moving scattered in a scattered pattern, no definite pattern, just scattered.
Sir,
Then we
please,
have the one.
I beg your pardon, sir. We did not join
Yeah.
on time. Please, yes, because we couldn't get the link. So we joined almost on, not we, I joined during the projectile.
Okay.
Yes, so please just do it a justice and explain them to me,
Okay.
please.
Did we see this point?
No, just from
Oh,
project.
yeah, I don't know. Maybe because we did a lot. But let me just see how I can just summarize from the image that is here. So from this image, we talked about the different types of motion, where I said there are four basic types of motion. Translational motion, which is a motion moving in a straight line. Probably the video will be available for you. So I'll see let me just give a summary so that when you watch the video again, you will hear me explaining it. So
Right.
translational motion is in a straight line, usually in a straight line. The rotational motion is about an axis, either about the horizontal or about the vertical. That's what horizontal motion is always like, in a circular path, or that is rotational motion. Then vibrational motion is any motion that is moving to and fro, going back, coming back, or going back, coming, or going up, coming down, going up, coming down, going up, coming down. When it's a constant forward and backward motion, like a constant to and fro movement, it's called vibrational motion. The to and fro movements, just like the devil. So random motion is the one that is scattered. Just it does not have it, it just scattered. So those are the types of motion, and these are the images for three of them, where we said this is representing the vibrational motion, the different types of vibrational motion. You could screenshot it or you wait for the class tomorrow. So because of time, there are some other activities that we need to handle up. That's the reason why I might not be able to keep on spending that time going through the whole stuff. So the video will be made available to you guys on Payling it tomorrow. Then rotational motion is circular or circular along the x-axis, circular along the y-axis. Then translational motion is either downwards, a downward motion, or a constant upward motion, or a constant motion to the left, or constant motion to the right. Is that what these kinds of motion are, right? So these are motions. These are the types of motion. So then we talked about linear motion, saying that we take attention. We talked about velocity, speed, and acceleration. Then we talked about what they call it, the different types of graph. Said there is distance time graph, velocity time graph, acceleration time graph. There are three types of time graph: distance time graph, the velocity time graph, and the acceleration time graph. And I gave images for each of the three of them. This was the image for the distance time graph. The explanation you will see it in the recording. Then the velocity time graph, this is what it looks like. You will get a full detail in the same recording. Then this is the acceleration time graph. Same detail you get it in the recording. So just do well to get it in the recording. It will be available for you guys tomorrow on Failingly. So then we went to the call, then I guess it was the area you came in, time motion and so on. So that's the whole concept for this week. That's all for this week under physics. And I believe we covered 3 weeks topic according to our syllabus for this night class. So if you've been consistent throughout these 3 classes, I can say you will be able to have gotten a grasp of most of the topics that you see in past questions and their likes. They will no longer be vague to you. So if you've not seen them, it's advisable that you go and see those videos. The videos are available so that you'll be able to keep up to track, because most of these things, they are built upon each other. This one, you might not understand the next one after it unless you go back to the one there and the one before it, so that you'll be able to catch up. So it's the end of today's class, and until we meet next time, I would like to say good night to everyone. Thank you all for attending the class. And God bless you.
Thank you,
Thank-
sir. God bless.
Thank you very much.
Take the leap. It's all in your